turn YouTube back on. Let's take a look at the 3 box plots of that data. Let's put them up together, three different box plots, okay? Now, FYI, when you look at the homework for ANOVA, I've got an Excel sheet hyperlinked in there that allows you to drop data in to an Excel sheet, and it makes box plots in Excel, which are way, way slicker than a box plot on a TI. They're also a total pain in the butt to create, which is why I created it and put it in Excel for you to use. If you ever need to make a box plot in Excel, you can grab that sheet from the ANOVA homework. If you ever need to use it. That's what I'm saying, if you ever need to use it. All right, plot 1, make it modified, why not? L1 and frequency is going to be 1. Because there's not a frequency distribution, we're just talking about the raw data, right? And do the same thing for plots 2 and 3, but make them L2 and L3. Fair enough? Yep, same exact plots for all of them, just make them L2 and then L3 for plot 3.
We want the excess to
L1 and then L2 and then L3, yeah. There we go, L3 is good. So if you look at the way they're set up, I gotta change that one, that was wrong. This one should be 1. There we go. L1, L2, L3 with frequencies of 1 because it's raw data, it's loose data. And then just take a look at it. Just take a look at it. So zoom 9 for zoom stat. There they are. This is where Excel is a little bit superior. The sheet I've written allows you to put column headings in, so you can actually label the graphs. Like this one's constant sound, this one's no sound, this one's random noise. So what I have to do now is I have to press trace, and I gotta go, okay, that's L1. I think so. So I got L1, which is constant noise, or constant sound. That's L2, which is random sound, and that's L3, which is no sound. So what do you think? Do any of the groups show a significantly higher, or appear to show a significantly higher or lower set of test scores than any other group, based off of this? We haven't done any testing yet, but does anything appear to be different? Kara, what are you looking at?
Well, on the top one, the Q1 is the same as the Q3 on the last two.
That's making me very happy to hear that right there. Check this out. What Carrie is looking at the boxes on the box plot. Q1, 25th percentile, is the same essentially as Q3 for the other two groups. That means 75% of the random noise data points are exceeding 75% of the other two. Excuse me, that wasn't random noise, that was constant noise. 75% of the constant sound are exceeding 75% of each of the other 2 data points. That's pretty fantastic. What do you think, Zoe?
I just had a question.
Yes.
Sorry. Why my graphs are different?
They are. Check your frequencies. Make sure your frequencies each say 1. I'm guessing that's what it is.
Check your L.
Yeah, L1, L. So basically, just press second Y equals, Zoe,
Okay.
and then make sure it looks like this. L1, L2, L3, 1, 1, 1.
Okay.
That should do it for you. Cool? So, I love that analysis, Carrie. I'm totally in favor of it. So it appears to us that maybe random sounds a little bit higher than the other ones. Paris, what are you thinking?
So you say 75% because the line matches up.
Yes, ma'am. Yes, ma'am. Because Q1 and Q3 are essentially lining up.
Okay.
Good. Like that very much.
Error window range.
Zoom 9.
I did.
Turn off whatever you've got in Y1 and Y2. Turn everything else off except for your plots. Zoom 9 should override all that stuff. So, the problem with this is, all we're looking at is the data. So I love Carrie's analysis, and I think it's a great place to start. How about random noise versus no noise? What do you think here? The median's higher, right? The median's higher. It's not as impressive looking as this one. And we also haven't adjusted for the fact that the min here is actually pretty far down. But what you guys are looking at, I love, is you're looking on median instead of just individual data points. But we still need a much larger, if you will, look at what's going on. We want to see if any one of these is significantly different than any of the other ones. So the hypotheses we're going to test, it looks like this one's different than these 2. It looks like it's higher. But the thing is, when you have 3 different data sets like this, there are 8 different things that could be true. This one can be higher, these 2 could be the same. This one, I should say higher. This one can be different, these 2 can be the same. They could all be the same. They could all be different. That one, you see what I'm getting at here? This is going to get really annoying really fast. So we're going to treat it like Goff in that respect. Turn this off for a second. Let's list out the hypotheses. We're going to treat it like Goff. We're going to treat it like Goff. Your hypotheses for ANOVA are pretty straightforward. Your null hypothesis, what do you, actually, let me ask you, what do you think the null hypothesis is going to be for this ANOVA test?
There's no difference.
That there is absolutely no difference in their averages. The average for constant sound is going to be the same as the average for random sound. Exactly. There's no reason to suspect any difference. That's the status quo. Equality always happens in the null. It's the same as the average for no sound. And I'm using mu because we're talking about the average test score, as Mary pointed out earlier. Yes. What's the opposite of that? Say that again, Jess.
There's going to be a difference.
Where? I love that.
At least 1%, at least 1%.
I love it. At least one of those averages is different. U1, at least one average is different. So do you see the similarity between Goff and ANOVA?
You want to do that to H1?
Yeah.
Instead of
Thanks. Sorry, YouTube world. Yes, call it H1.
I passed the test.
You can all go home now. So the question is at least one different? What it will not answer is which one, if there is a difference. So, and I know this gets confusing, and I made you guys flow charts in the Goff and ANOVA homework. And if you look at your homework, you'll see there's a PowerPoint, maybe Excel actually. It's either a PowerPoint or Excel, I forget which. But it's a flow chart that walks you through the steps for these tests. And again, that's more for when you take this class outside of class. So if you're ever running one of these, you probably will experience ANOVA in a daily basis, especially depending on what kind of field you're in. Sociology, psychology, early childhood, ANOVAs are all over the place. So being able to deal with ANOVAs and their post-test is pretty important. I'm not going to crush you next week by making you do them in class, that's dumb. But knowing what to do when you get to certain points is important. So I made a flow chart for you. Keep that, it's always going to be posted online, you can always get to it. So just know it's there for your reference if you need it. Some textbooks kind of do a pretty good job of hiding that in their appendices, so I made it nice and colorful and arrow pointy and green and pink and things like that. Okay?
So we're not going to be testing over this?
No. We're going to test to see which one of these we believe.
No,
But if we hit this, then we don't know which one causes the difference.
Are we going to be tested over this material?
Oh yeah, but not the post-testing. When you'll see what I'm talking about in a second. So here's how you actually run an ANOVA test, and this is why we don't do it by hand, ever. Just FYI, some of you that take OSU stats, they make you do this by hand. It's the heads up. In case you need it, it's here for you. So the first thing, here's your hypotheses. So the first thing you do is you calculate the individual sample averages. So right now, constant sound has a higher average than either random or no. So our initial gut feeling is yeah, okay, something's up. It looks like 6 is higher than 4, which is higher than 3.375. But the problem with that is that's strictly descriptive. Essentially, what we have to do is make a confidence interval around all 3 of those and see if any of them overlap. But what's the problem with doing that?
You lose your
You lose confidence, just like we always talk about. You can't run 3 individual t-intervals because you'll lose your confidence. So we create what's called X double bar, which is a direct copyright infringement over a symbol I made up in 243. I'm not pissed or anything. So what that does is it basically creates the average of the entire data set. And when I say the entire data set, all 24. So it's all 24 averages, if you will, divided by 24, and then you come up with, what is it? I don't know what that's equal to. It's equal to that, I guess. Then you do, if you will, they call it the sum of squares of the treatment, which is this monstrosity. Okay, keep that following in the back of your mind. Individual sample variances. Sum of the squares of the, you see what's happening here, friends? You're starting to get that bile taste in the back of your throat. Yes. This computation is hellish. It's absolutely hellish. But what it's doing is, all it's doing, because I want you to know what the black box is going to kick out actually. It's looking at the variance of the data 2 different ways. It's looking at the variance inside the entire data set without reference to the 3 groups, and then it's looking at the 3 groups' individual variances. That's why it's called analysis of variance. And it tries to see if there's a difference in those variances. If there's a difference in the variances, then there's a difference in the averages. And that's what's brilliant about it. That's what's brilliant. If there's a difference in the variances, there has to be a difference in the averages. Very, very clever. Extraordinarily clever. However, I don't want you to have to go through, we're not even done yet. You gotta go through all this stuff. So, ignore that. Ignore that. I mean, if you ever need it, it's right there for your reference. Grab your TIs. You've got the tool you need. You've got the tool you need. There's our box plots. All we basically need is we need a test to take us to the inferential part of this. That's descriptive. That's the samples look like they're different. Will that sample hold up if we treat it inferentially? Stat tests. Go find ANOVA. Very last one. ANOVA. Grab it, and then just put the lists in separated by commas where your data is. L1, comma, L2, comma, L3. Yep, stat test, it sounds like it's the very last one. This takes care of all of that computation I just went through in 2.5 minutes. And it's not worth going through. The big thing is to decide if the variances looked at two different ways are similar or different. Oh, Mercury, very nice. All right, there is a lot of stuff up here on this screen. A lot of stuff. However, the only thing you guys have to look at is the very first two. Everything else are the computations. Everything else are the computations, of which, if you're interested into what the computations are actually doing, and you're more than welcome to be, you can look at that write-up that I've got online posted for you in the enrichment page, like where I put everything else, in case you're interested. All those sum of squares and mean square errors are down here. All those beautiful errors are down here. But here's the only two things you have to look at. F is the test statistic. FYI, the smallest value that test statistic can have, or I shouldn't say the smallest, the measure of the test statistic you compare to is the value 1. And the reason it's 1 is if there's no difference in the variances, that means they're the same. And if you divide a number by itself, you get 1. So deviation from 1 is what we're looking for with an F test. So the test statistic is about 3.6, and this is the problem with the ANOVA test. That doesn't tell you anything. You have to slap that up onto a curve. The curve essentially looks like a goodness of fit curve. But rather than have you do that, and the TI doesn't grab it for you anyway, just look at the p-value that goes with it. What do you think? It's less, that's the key. It's less than 5%, which means it looks like H1 is the hypothesis. Ian, answer that question, friend.
No.
You sure?
Yeah.
Oh, come on. No. You don't think? Maybe. Ish. Think about it. I want to hear, even if you think it's not, I want to hear, Bob, go ahead.
So you're saying it's less than 5%, so that means that there's no change in
It's less than 5%.
So there was.
Who are we going to believe? We're going to believe this guy.
Okay.
It tells us at least one of those groups is different. It doesn't tell us which ones, but it tells us at least one is different. That's all it tells us. At least one of the averages is different. For next week's test, check. You are now done. You are now done for next week's test. In reality, you would then want to go back in and find out which ones, inferentially. And then you would use the post hoc test, which I have outlined on your homework sheet. If you ever need them, they're all there waiting for you, if you ever need them. But for next week, you would stop right there. P-value less than 5%, therefore, at least one of those averages is different. Go ahead, Zoe.
So we don't need to do anything with the F?
No, the F is the test statistic. So when I ask you to give me the test statistic and the p-value, you write down the test stat is F equals 3.6-ish. And the p-value is, put whatever you want, less than 5%. That's fine too. So it appears that at least one of those averages is different. Doesn't tell you which one, just tells you at least one is different. Is that fair? Yeah. And the reason it's called F is this guy Fisher, he's the one to give up the test. It's a brilliant test. It really is. I would have never thought about looking at variances to test averages, but it's one of the most common statistical tests. T-tests and ANOVA are the ones you're going to see over and over again in research. In your lives, in the media, you see Z-tests all the time, and occasionally GOFs. So, as far as parametric tests go, ANOVA and T-tests are really all over the place. They really, really are.
Are you going to want us to identify?
No.
You're going to
Which one?
Run the ANOVA on.
I'm not going to say I'm not going to run the ANOVA. You're going to know to run the ANOVA.
I will.
Yes, that's where Thursday comes in.
I mean, I couldn't know.
That's That's what Thursday is all
Can you
about.
say like rhymes with blova?
I do that occasionally, if you've noticed. Rhymes with standard abbreviation. No. What we're going to do on Thursday is present you guys with a whole bunch of data sets. And when I say a whole bunch, I mean 5. One of which fits each of the 5 tests we're talking about. And then your job is to go through them and realize. Now, there are certain giveaways to know that you have to run an ANOVA for this. First of all, there's 3 groups. That makes it either a GOF or an ANOVA. And then you have to ask yourself, oh, what variable am I testing? Oh, it's not percentages. Therefore, it has to be, see what I'm talking about?
See, I guess I haven't gotten that far in my
That's
brain
what,
where.
and Thursday we'll do that. And we're going to do that that's what Thursday is all about. Zoe.
Are you gonna write on the board again, like, which test to use, because the other 3 are confusing?
Oh, that's what, and again, Thursday, that's all we're doing on Thursday. I'm going to put the big flow chart up with all the individual tests and which tests go on. Yeah, that's what Thursday is. Thursday's a big, you won't need it, you'll know it by then. You won't, you'll know it by then, I guarantee you. Oh, we're only adding one more thing. We're only adding one more thing. The ANOVA. That's the chronic vote. Susie. Hang on guys, hang on.
So it needs to be type 1 or type 2 errors?
Again, this could be a potential type 1. We're saying that at least one's different. Maybe we're wrong. Maybe they're all the same. We belong on that curve. That's pretty close to 5%, isn't it? That was pretty close to 5%. So, again, I've laid off the error identification only because I think you have assessed you to death on that.
Good, I was just guessing.
What's that?
Good, I was just guessing on the
You're
hair.
getting them all right? The
Nope.
chance of that...
Actually, doing pretty good.
Putting to 0. We're maxing his crops. Darla, go ahead.
I was just going to say, on that p-value, if we round it up, it would be 5%.
That's exactly correct, but it is less than 5%.
So if we
Pre-rounding.
round up and
Say that again.
if we were to round up and
But if you
we
said that
split
that's equal to 5%, it's not. It's actually less than 5%. But I love your point, though, Darla. I love your point in that. I would answer this question 2 ways. I love your point in that you're a little bit skeptical because it's so close to 5%. So what would my vote be to you? If you thought that there was a difference,
Run the test again.
run the test again with more data, as long as the data is good. If there is a significant difference, the good. The curve is going to get tighter and taller, and that p-value is going to get smaller and smaller and smaller because the standard, or the, if you will, the measure of variance ratio is going to go out. Good, that's one answer. I find data on your exams that are obvious. There's plenty of ANOVA data out there that I can track down that's got very, very small or very, very huge p-values. I won't give you one that's like 4.98. That's a total bastard move. No, it's a total bastard move. And you see what the responses I just got from you guys, oh, go get more data if you believe there's a difference. That's all I care about. That's what I care about. I don't want to make a tricky test. I saw another hand. Jared, go ahead.
So, GOF test is if we have
Proportions.
proportions, and this is if we just have the data.
Yes, if you have averages. So think about this. The entire class has been back and forth, proportions and averages. Confidence interval proportion, confidence interval and an average. 1 proportion, 1 average. 2 proportions, 2 averages. GOF, 3 proportions, ANOVA, or 3 or more proportions, ANOVA, 3 or more averages. Everything's back and forth. I've tried to keep it symmetric. That's why I left variances off. That's why I'm dumping into attendance testing. I try to keep everything kind of, keep that symmetry in the class going back and forth. Fair enough? And the reason that you might think to yourself, wait a minute, you said there's going to be 5 tests on this exam next week. Why not 6? Because you did 1 last exam. 1 proportion, you nailed on the last exam. I'm not going to bring that back. It seems kind of dumb.
I actually didn't think why not 6.
You didn't? Oh, okay. Sorry. I'm sorry, I said it then. Fair-ish? So this is the... Mary, go ahead. What's in your mind? Mary, I'm sorry. I try to read faces. When I start seeing them look panicked and in pain, I try to...
I thought why not 6?
Oh, okay, me too. Because you already did the last exam. Ian, that question, you sure?
Yeah.
Okay. All right. Keep thinking about it. Let's run another ANOVA just to make sure. I mean, it's fairly straightforward. It's doing all the work for you, and all you've got to do is run the computation in the machine and interpret the p-value, which is all I care about anyway. I'm not going to test you on running that thing by hand. It's ridiculous. It's stupid. It's dumb. So your guys' pick. Do you want to do soap and bacteria on hands?
I do. Yeah.
Or the other one is forcing young children to walk and seeing if doing walking exercises and seeing if they walk earlier due to practice.
I think it makes them pigeonhole.
Okay, well, we're actually not testing that, believe it or not. We're testing. Well, we could, because that's a measure of an angle, which is continuous. We could test it using an ANOVA. So your guys' call: bacteria on hands or children walking. Oh, well, I heard a bunch of walking. Let's do walking. This is on the other page, page 3. This was in Science Magazine. I love this one.
I still couldn't get rid of that error.
Okay, everybody read this. Let me figure out what's going on with Ashley's errors on the TI. There's something going on because every time I press the arrow, what is this? Thank you. So it's processing something. I wonder how to turn the wall off sometimes. Oh, now it is. Alright, so let's just manually change your window range to something else. And that works just fine. There you go. I just changed your Y min and your Y max were the same, and for whatever reason, Zoom 9 wasn't overriding that, which it should do. So I just changed. I went into your window and changed your Y min to be less than your Y max, and then it worked just fine. Yes.
On these, do we still have to do the it appears or does not appear?
You have to say it in some way. So at the end, I'm going to ask you for a conclusion. So for this one, it appears that at least one of the test averages is different. And that's all you have to say. It appears at least one of the averages
We
is
have to
different.
write it this time.
You do. And that's okay because you're ready for it.
Yeah.
You're totally ready for it now.
Yeah.
Yes. Yes, you are. All right. So, what are we doing in this study? Oh, good. Well, that's what you're doing in the data analysis of the study, Bob. Why was the study motivated at all in the first place?
Parents were worried there's something wrong with it.
Because we want our kids to walk more quickly. Why any parent would want that is beyond me. They're so easy to keep track of when you can put them on the bed and let them just lay there on their back gurgling. When Max started walking, I started getting more gray. So anyway, we're interested. We're interested to see if there is a difference. If we give them walking exercise, 12 minutes daily, beginning at the age of 1 week. That blows me away. 1 week. I mean, what do? Don't poop on yourself. And lasting 7 weeks. Other exercises, but not the specific walking exercises. No exercise at all. So this is one control group, right? One control group, no exercise, but we're watching them once a week. And then the last group was a control group, but only watched at the very end of the study. So this is interesting. You've got 2 experimental groups and 2 control groups. So again, if you had 1 experimental group and 1 control group, right, 1 and 1,
Oh, yeah.
what would you do? If you only had 1 and 1, you would just do a 2-sample t-test, wouldn't you, Jamie? Because you only have 2 groups. That's a 2-sample t-test. What an ANOVA is a more than 2-sample t-test, essentially. It's a t-test for 3 or more samples. But if you only had 2, could you run an ANOVA on 2? Yes, you could. You could, but nobody does because it's like curing a headache by chopping off your head. It gets the job done, a little messy. So, not to use it, sorry about the negative. Yeah, anyway. So anyway, well, we have 4 groups. So we're going to run the ANOVA. The only problem with the TI in this case is I would love to graph all 4 of these like we did with box plots, but you can't. Because you can graph 3 things and no more than 3 things at a time, which sucks. So, again, I gave you, in your homework for ANOVA, there's a spreadsheet link in there that takes you out to a box plot generator for any number of groups that you want. So, if you ever need to make box plots in Excel, you have a couple choices. You can either Google how to do it, which is what I did, because there's no built-in for it, and then I made that up for you, or just pull off that box plot and edit it and make it your own. That's why I gave it to you, just so you could use it if you ever need a box plot in Excel, which you might need someday if you use Excel quite a bit. Right? So, let's get some hypotheses to test. Yes. So, what's our null, friends?
There is no difference.
There's no difference at all in the groups. No difference at all in the groups. So the average length of time it takes a kid to start walking with the exercise number 1 is the same as the walking with the exercise number 2, which is the same as the walking with no exercise. 1, which is the same as the walking with no exercise. I'm talking Bill Cosby up here, I apologize. And the pudding pops! All the averages are the same.
This would be at least one.
And frickin' and the frickin'.
The H1.
What's the opposite of that?
At least one is different.
Yes, at least one's different, but it won't tell you which or which ones. But we just know at least one's different. So to re-answer Ashley's question, at least one is different. One average is different. To re-answer Ashley's question, the only thing I'm not going to ask you to do with GOF and ANOVA is if there's a difference, go back in and find where the differences are. You probably will have to do that in your careers. Just put that out there. But for next week, to put your mind at ease a little bit, there's enough to keep track of rather than this too. Please, Ashley.
Would you run a t-test?
Yes, but you have to correct the p-value again, just like you did with the GOF.
Okay.
And I got it all. It's in your homework if you ever need to see it walk through.
Okay.
It's in your homework. It's all ready to go for you. If you ever, I kind of want you to use this class as a stepping stone into your careers. When you need statistics, come back, find the stuff, and pull